Good day to you, friends. Now we're going to talk about linearizing a function. So we use linearization as a method of approximating a value when it's pretty hard to find the equation of the tangent line, or it's hard to deal with a specific function. And so we used it maybe a little bit in Calc 1, but we'll use it more here in Calc 3 because obviously we're dealing with two variable functions, which are more complicated. So the idea behind linearization is that we approximate the values we're trying to find by using a simpler function. So the idea, here we have some paraboloid, and you can see it touching the tangent plane. And if we think about this second picture as being more zoomed in, you begin to notice that the paraboloid and the tangent plane are touching. They almost seem to be closer in shape. And then if we zoom in right here, even more on this one, and I know it's kind of hard to see, but you see that tangent plane and the paraboloid are almost identical. And here's another but similar picture, the same idea. So zooming in on this one point of interest, and as we get closer and closer and our scale becomes smaller, the perspective is that they start to really look like they're the same space. So the idea is if we can zoom in and we can get close enough to the value that we're interested in finding the derivative or whatnot of, then we can use this linearization to help us get a close enough approximation. So here we have a definition for the linearization of a two-variable function at some point, as long as the function's differentiable. So that linearization, L, is equal to the function evaluated at that point plus the partial of x at the point times x minus that x naught plus the partial of y at the point times y minus y naught. And so if we calculate this linearization correctly, we say that that linear approximation is close enough that it's equal to the function value. Okay, so this represents the standard linear approximation of a function at that point x naught, y naught. Now let's do an example. For this example, we're going to find the linearization of the two-variable function at the point 3, 2. Our function is x squared minus xy plus 1/2 y squared plus 3. So in order to do this, we look at our definition. And inside the definition, we need the function evaluated at the point, and we need the partial of x as well as the partial with respect to y at that point. So I'm going to find those first. First thing, f of 3, 2 is 3 squared minus 3 times 2 plus 1/2 times 2 squared plus 3, which gives me 8. I also need my partial of f with respect to x at that point. So treating y as a constant, the derivative of 3 is going to be 0. This is just a constant, so those go away. I only need to consider my first two terms. This means I am calculating 2x minus y, and I need to evaluate that at the point 3, 2. So 2 times 3 minus 2 gives us 4. Similarly, the partial derivative of f with respect to y, that means x is a constant, this 3 is a constant, so we treat the other values as, this x right here is a coefficient, so I'm going to have negative x plus y, and we need to evaluate that at 3, 2, so that is negative 3 plus 2, we get negative 1. So then by our formula, the linearization of this, my linear approximation, is that function value 8 plus my partial with respect to x, 4, and I'm going to say x minus 3 plus the partial with respect to y, which is minus 1, and then we'll have y minus 2. And simplifying that, we've got L of xy is 8 plus 4x minus 12 minus y plus 2. We end up with 4x plus y minus 2. So we're saying this is a close approximation. This plane is a close approximation to the function at that point. How close? Well, we're going to talk about error in a minute, but let me pull in my visual. So here is my surface. And we're saying at that point, we can create this plane. And if I were to zoom in really, really, really close to that point where I was just looking at the regions very, very near that point, then this plane is a close approximation of that surface. So since this linearization, this plane here is an approximation, it is important to be able to determine that margin of error, right? So we have a definition for error here that we're going to talk about. So if we want to calculate the error for our standard linear approximation, and we have all these things that we have to say first, but we say the function's continuous. We can find first and second partial derivatives throughout an open set containing a rectangular region R, which is centered near my point. And so if M, this upper bound value, which is going to be the largest value determined by taking these partial second derivatives of the function in that rectangular region, we can calculate the error E. So this is something very similar to what you did when you were talking about like trapezoidal rule and Simpson's rule in Calc 2. We calculated the error to see how close we were getting to that actual integral. So here we're going to be saying, well, we can calculate the error and determine how accurate this linear approximation is. And so this is just saying, hey, that's our standard linearization definition. All right, so this is the inequality. And then this M value comes from taking these partial second derivatives, right? That's the maximum of those is going to give us the M. And so if we want to make our error small, then this prescribed distance away from my X and Y values also needs to be significantly small. So that's where we're talking about this open set, this rectangular region. So we have this small area near the point that we're using for our calculations. And if these guys are small, then this error is going to be even smaller. So for the second example in this video, we're going to find the linearization, which is quick and easy, at a point, and then we're going to determine this upper bound M and calculate that error. For this example, we're going to find the linearization L for the function, the multivariable function f, at the given point P naught. So my function here is listed out 1/2 x squared plus xy plus 1/4 y squared plus 3x minus 3y plus 4. We have our function, quite complex. We don't want to deal with it, so we're going to find a linear approximation. We're going to deal with it at our point P naught is 2, 2. And once we've done that, then we want to find M, that upper bound for the magnitude of error, or that error permitted in the approximation, right? So we're going to come up with an L of x, which is pretty close to f of x on some rectangular region. And so here we're saying x minus that initial 2 and y minus that initial 2. This is creating my rectangular region, and I'm only allowed to move 1/10 of a value off in any direction. So positive plus or minus 0.1 in the x and plus or minus 0.1 in the y. So it's creating a rectangular region off that point 2, 2, where we can only go, plus 0.1 and minus 0.1 in either direction, up, down, left, and right. Can't draw it that way. All right, so that creates my little rectangle. And then we're going to calculate, as long as we are using the linearization within that region, what will the error be? So step one, first thing we need is our linearization. And that means I need the function value, the partial with respect to x, as well as the partial with respect to y, both evaluated at that point. So my function value, if I go and I plug 2, 2 in, I'm not going to bother with this calculation. I'm just going to write 11 because you guys can all plug 2 and 2 in here and tell me that that's equal to 11. All right, my partial of the function with respect to x, and we're going to evaluate it at 2, 2. So that means treat y as a variable. Here I have just x plus, there I get y, constant. This turns into a 3, and the other two are constant. So I have x plus y plus 3, and if we evaluate that at 2, 2, we get 7. We'll do the same thing, partial with respect to y at that point, treat x as a constant. So I get, this guy goes away, this one I get x, this becomes 1/2 y, goes away, -3 goes away. So I have x plus 1/2 y minus 3, and we need to evaluate that at 2, 2. Plugging that in, I get out 0. Therefore, I can write L, my linear approximation, and that's going to equal 11 plus 7 times x minus 2 plus 0 times y minus 2. And of course, that last term is going to go away. So I have L xy is 11 plus 7x minus 14, or L of xy is 7x minus 3. So this is my linear approximation, or my linearization. All right, so now we want to calculate the error for our linearization. And recalling our definition, we need these second derivatives. We're going to calculate 3 second derivatives, and the largest absolute value one, that's going to represent my m in my error formula. So if I go and I take this derivative up here, I got fx, and if I take the derivative of that again with respect to x, that's going to be 1, 0, 0. I get 1. Partial of y with respect to y. So 0, 0, I got 1/2. And if you recall, if I take this partial with respect to y, I'll get 1. If I take this partial with respect to x, I get 1. And we know those are going to be equal. So we also know that f of xy equals f of yx, which is 1. So we have to look at the absolute value for all of these. So sometimes you'll get negative numbers here. We're looking at the largest absolute value one, and in this case, I can see that my m value is going to equal 1. So thus, sound all professional, thus the magnitude of the error needs to be less than or equal to, this is my formula, 1/2 m, my m value is 1 that I just calculated, times x minus the point 2 plus y minus that point at y, 2 squared. Now, how far off were we allowed to be at a maximum? So we go back up to what was defined as our rectangular region. The maximum value that these two numbers could be, x minus 2 and y minus 2, could be a tenth of a position or a unit off. So I say less than or equal to 1/2. I'm going to let that 1 go away, and I have 0.1 plus 0.1 squared, which is 0.2 squared. Squaring 2, you're going to get 4, but with 2 places behind the decimal. So I've got 0.04 over 2. So now I know that the magnitude of my error, if I am within 1/10 of a unit from that ordered pair 2, 2, is going to be less than 2/100ths of a difference off. And so that's how we can find this linear approximation, the linear approximation, or rather the standard linearization for the function. And we can determine our error. All right, so in the next video, I'm going to do this again, but just with a 3-variable function. So follow up with that video if you want, or you're good here. But don't worry, I've always got more for you. As always, email me if you have any questions.